The elements in the group 2 of the periodic table except beryllium are called alkaline earth metals. The energy to remove the outermost electron from an atom is called as ionization enthalpy. After removing the second electron, it will reach noble gas configuration. The alkaline earth metals form more extensively hydrated compounds than those of alkali metals. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. Today, we are starting up session 3 from the chapter S block elements. In the last session, we have discussed about anomalous properties of lithium, diagonal relationship, general characteristics of the compound of the alkali metals. These are the properties of S block elements we have discussed in the previous session. In this session, we'll start about group 2 elements which can also be called as alkaline earth metals. Also, ionization enthalpy, hydration enthalpy, physical properties and chemical properties of group 2 elements, that is alkaline earth metals, we'll discuss in this session. Group 2 elements. Introduction. The elements in the group 2 of the periodic table except beryllium are called alkaline earth metals. In the order of increasing atomic number, the group 2 elements are beryllium, magnesium, calcium, strontium, barium and radium. They are soft and silvery metals. Each element in this group has a tendency to lose 2 electrons to form doubly charged positive ion, that is M2+, which has the stable electronic configuration of its neighboring noble gas element in the periodic table. What they are telling? Group 2 elements also called as alkaline earth metals, and in the order of increasing atomic number, because it is in group 2, it will increase its atomic number, and the elements are beryllium, magnesium, calcium, strontium, barium and radium. They are soft and silvery metals. In name itself will show it is a metal, and like group 1 elements, it will also lose some electrons, but not exactly one. It will lose 2 electrons and it will form positive ion or cation will form M2+. Okay. And it will be having stable electronic configuration like noble gas element in the periodic table. Next, electronic configuration of alkaline earth metals. These elements have 2 electrons in the valence shell. Their general configuration is written as NS2, where N represents the valence shell. This is beryllium, 4 atomic number, 2s2, magnesium 12, 3s2, calcium 20, 4s2, strontium 38, 5s2, barium 56, 6s2, radium, this is 7s2. Means after noble gas configuration, it will end up with the valence shell of complete configuration. Next, ionization enthalpy. We know what is ionization enthalpy. The energy to remove the outermost electron from an atom is called as ionization enthalpy. Due to fairly large size of the atoms, alkaline earth metals have low ionization energies comparative to p block elements. Down the group, ionization energy decreases as atomic size increases. As atomic sizes keep on increasing, the ionization enthalpy will decrease. Down the group, size will increase. So, ionization enthalpy will decrease. This is due to new shells are being added and increase in the magnitude of the screening effect of inner shell electrons. Why it is getting decreasing? Because when atomic sizes keep on increasing, the new shell will added for the atom. When new shells are added, the shielding effect will also increase to protect the inner electrons. So, obviously, the ionization enthalpy will decrease. Members of group 2 have higher ionization energy values as compared to group 1 because of their small size. Comparative to group 2 and group 1, group 2 is having higher ionization enthalpy because it is having smaller size. And with electrons being more attracted towards the nucleus, correspondingly they are less electropositive comparative to alkali metals. We know one point, from left to right size will keep on decreasing, but from top to bottom in the periodic table, that atomic size will increase. So when comparative to group 2 and group 1, little bit group 2 is having lower size, so it is having higher ionization enthalpy. Also, the electropositiveness also from left to right it keep on decreasing. When comparative to group 1 and group 2, the electropositivity is less in group 2 comparative to group 1. Okay, this is ionization energy in 899, this is 737, 590, 549, 503, 609, it is keep on decreasing. Although ionization enthalpy first values of alkaline earth metals are higher than that of alkali metals, the second ionization enthalpy values of alkaline earth metals are much smaller than those alkali metals. This is so because in alkali metals, the second electron is to be removed from a cation which has already acquired noble gas configuration. Why it is very small, that is the IE2, that is second ionization enthalpy is small because after formation of one cation, it is difficult to remove that second ion from the noble gas configuration. So, whereas in the case of alkaline earth metals, the second electron is to be removed from the outermost electron from a monovalent cation. But in the alkaline earth metal, it can easily remove the second electron also, because after removing the second electron, it will reach noble gas configuration, which has to lose one electron to attain noble gas configuration. Thus, the second electron can be removed more easily in the case of group 2 elements than in group 1. In the group 1, if you remove one electron, it will attain noble gas configuration. But in the second group, if you remove 2 electrons, it will attain noble gas configuration. So, ease of removing electrons in the group 2 is having 2 electrons, not in first group. Next, hydration enthalpy. Alkaline earth metals have more hydration enthalpy than alkali metals because the size of alkaline earth metals is smaller than that of size of alkali metals. Due to the smaller size, hydration enthalpy is more in alkaline earth metals than alkali metals. Reason: the charge on alkali earth metal ions, that is M2 plus, is greater than alkali metal ion. As a result, the nuclear attraction increases, resulting in the smaller size of alkaline metal earth metal ions compared to that of alkali metal ions. Hence, the hydration enthalpy of alkaline earth metal ions is larger. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decrease with increase in the ionic size down the group. See here, Be2 plus. This is Mg2 plus greater than Ca2 plus greater than strontium 2 plus greater than barium 2 plus. First we have to understand beryllium means it is usually beryllium is having 4 atomic number. It is 2 electrons has been removed means it will become beryllium 2. Like that it will be keep on decreasing here. Okay. Since the hydration enthalpies of alkaline earth metal ions are larger than that of alkali metal ions, the alkaline earth metals form more extensively hydrated compounds than those of alkali metals. We know that one point, now we have understood, alkaline earth metals are having more hydration enthalpy than alkali metals. Because of that point, the second group elements will form more hydrated compounds than group 1. MgCl2 and calcium chloride exist as magnesium chloride hexahydrate and calcium chloride hexahydrate, while sodium chloride and potassium chloride do not form such hydrates. Okay. The group 2 elements will form hydrated compounds, but group 1 elements will not form that much hydrated compounds. Next, atomic and ionic radii. The atomic and ionic radii of alkaline earth metals are smaller than the corresponding members of the alkali metals. This is due to the fact that group 2 elements with higher effective nuclear charge allow electrons to be attracted more towards the nucleus. This reduces the size of atomic and ionic radii. On moving down the group, the radii increases due to gradual increase in the number of shells and the screening effect. What they are telling? The atomic and ionic radii of alkali earth metals are smaller than the corresponding members of alkali metals. Because size is getting decreased means obviously atomic radii and ionic radii will also get decreased. When it is moving from left to right. This is due to the fact that group 2 having high effective nuclear charge. Yes, it is having high effective nuclear charge because size is less. The nucleus and the electrons will get the effective nuclear interaction is having more. Okay. See here, physical property, atomic radius from beryllium to radium, it keep on increasing. Ionic radii also it keep on increasing. Okay. It is down the group, right? So, next physical properties. Due to the presence of 2 electrons in the valence shell, stronger metallic bonds are formed which result in the close packing of the atoms. Due to 2 electrons are present in the valence shell, it will form nice metallic bonds with close packing of the electron atoms. Due to the presence of stronger metallic bonds, alkaline earth metals have higher melting points, higher boiling points, higher densities and harder than corresponding alkali metals. It will form strong bonds, means it need to have more melting point and more boiling point to break it. So, density is also more harder than alkali metals, it needs high melting point, high boiling point, everything is strong. Next characteristic, flame coloration. Except beryllium and magnesium, the alkaline earth metals impart characteristic color when heated on a Bunsen flame. This is due to the ease of excitation of their valence electrons. Why usually electrons or why usually elements will impart color? Because of the excitation of its electrons. So, except beryllium and magnesium, other elements which are present in group 2 will impart color. When elements are there, compounds are introduced to flame, the electron absorbs energy from the flame and gets excited to higher energy levels. When these electrons return to their ground state, they emit absorbed in the form of visible light having characteristic wavelength. We know that when the electrons have been excited, it will come back to its original state, but with some wavelength. Here, that wavelength will show in the form of visible region with some color. Depending upon the wavelength of light emitted, different colors are imparted to the flame. Salts impart characteristic colors to the Bunsen burner. Okay. Here, calcium, brick red, strontium, crimson red, barium, apple green, radium, carmine red. These are the elements which impart color when it has been projected to flame. Next, chemical properties. First one, reactivity towards air and water. Beryllium and magnesium are almost inert to air and water because of the formation of oxide layer on the surface. Beryllium and magnesium are almost inert, means it does not react that much with air and water because it will form oxides on the surface. Powdered beryllium burns in air to form beryllium oxide and beryllium nitrate. When beryllium is treated with air in the high temperature, it will form beryllium oxide. When beryllium is treated with nitrogen, means it will form beryllium nitride. Likewise, magnesium being more electropositive burns in air with dazzling sparkliness to form magnesium oxide and magnesium nitride. It will also form nitride and oxide with the dazzling sparkness. Calcium, strontium and barium react readily with air to form respective oxides and nitrides. Calcium, strontium, barium reacts vigorously even with cold water to form hydroxides. Other elements like calcium, strontium, barium react with air to form oxides and nitrides. With cold water it will form hydroxides. Next, reaction with hydrogen, that is formation of hydrides. All the alkaline earth metals except beryllium combine with hydrogen directly on heating to form metal hydrides of formula MH2. This is any alkaline earth metal reacting with hydrogen. In the high temperature, it will form metal hydride. The hydride of beryllium can also be obtained by reduction of beryllium chloride with lithium aluminium hydrogen. See here, beryllium chloride plus lithium aluminium hydrogen, in the presence of high temperature, it will form beryllium hydride, lithium chloride and aluminium chloride. Both beryllium hydride and magnesium hydride are covalent compounds having polymeric structure, whereas hydrides of other elements of this group, that is calcium hydride and strontium hydride and barium hydride, are ionic. All the hydrates of alkaline earth metals react with water, liberating H2 gas and thus act as reducing agents. What they are telling, both beryllium hydride and magnesium hydride are covalent compounds having polymeric structure, whereas hydrates of other elements in this group are ionic in nature. Okay. And these hydrates of alkaline earth metals react with water to liberate H2 gas, that is hydrogen gas, and will act as a reducing agent. This metallic hydride, that is alkaline metal hydride, react with water and it will form metallic hydroxide with the liberation of hydrogen gas. Thus, calcium hydride is called hydrolith and it is used for the production of H2 by action of water on it. Next, reaction with halogens. The alkaline earth metals react with halogens at elevated temperature to form halides of the types Mx2. This is metal, this is halogen, it will form metal halide. You know metals from the alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, and here halogens, chlorine, bromine, fluorine, iodine. Next, reactivity towards acids. The alkaline earth metals readily react with acids liberating hydrogen. When alkaline earth metal reacting with hydrochloric acid with any other acid, it will form metal halide plus hydrogen gas. Next, reaction with ammonia. This is salt. Okay. When metal is reacted with hydrochloric acid or any acid, it will form salt plus hydrogen gas. When reaction with ammonia, like alkali metals, the alkaline earth metal dissolve in liquid ammonia, the blue-black solution from which ammoniated ions can be recovered. Here metal will dissolve in ammonia, it will form ammoniated ions. Next, reducing character. The alkaline earth metals are weaker reducing agents than alkali metals. Both alkali metals and alkaline earth metals are reducing agents which will donate the electrons to the electron recipient compounds, but in the comparative way, alkali metals are strong reducing agent, alkaline earth metals are weak reducing agent. Because of ionization energies of alkaline earth metals are higher and their electrode potential are less negative than the corresponding alkali metals, because it is having less electrode potential as well as ionization enthalpy is also high. Their reducing character increases down the group as in the case of alkali metals. This is because of the tendency to lose valence electrons increases down the group. Even though beryllium has less reduction potential than the other alkaline metals, it is a good reducing agent due to its high hydration energy and large value of atomization enthalpy. Here beryllium will act little bit differently when comparative to other alkaline metals. It is having less reduction potential though, but it is a good reducing agent because it is having high hydration enthalpy. Next, uses of alkaline earth metals. Beryllium is used in the manufacture of alloys. We have discussed what are alloys in the homogeneous mixture of metals. Copper beryllium alloys are used in the preparation of high strength springs. Metallic beryllium is used in the making of windows of X-ray tubes. Magnesium forms alloys with aluminium, zinc, manganese and tin. Magnesium aluminium alloys being light in mass are used in the aircraft construction. Magnesium is used in the flash powders and bulbs, incendiary bulbs, bombs and signals. A suspension of magnesium hydroxide in water is used as antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperatures, have often been used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example in the treatment of cancer. See here, from health, there is a wide application in health also, like medicine field, medical field, also in the mixturing of alloys, good spring or good strength metals you can form, also in the toothpaste field, or also to remove air also from vacuum tubes. So this is about the complete introduction part of alkaline earth metals and the uses of alkaline earth metals. In the next class, we will discuss about general characteristics of compounds of the alkaline earth metals, oxides and hydroxides as well as halides. I hope you have understood completely whatever I have taught today. So, we will meet in the next session. Thank you.